Hello everyone, and this is Radu, and I'm Rafal, and welcome to the second community theater talk right now. So we're Sematics engineers and consultants, and we would like to share a story today. So we containerized our JVM apps, and then it didn't go as it should, and we would like to tell you why and what to avoid in order to avoid the same mistakes with it and our client did. So our migration went the usual path, right? We wanted better resource usage to save some money to be able to use it elsewhere. We also wanted to avoid configuration drift so that our containers are the same, like in QA, production, and test environment, so no like oops are happening. In addition to that, we wanted easy to scale, upgrade, and deploy infrastructure so we can react to metrics, both upscale when it's needed and downscale when it's needed as well. But of course, there is always something that's stands in line and doesn't want to work as it should. And in our case, it was Java. So initially, when we were actually trying to deploy our stuff in orchestrated environment, in Kubernetes actually, not everything was smooth, as you can imagine. Our images were big initially. We set the wrong heap sizes, so the constraints were not right on the containers. What's more, constraints on the containers actually showed us that we have some amount of memory leaks, so we had to fix our applications. So that's something that was highlighted during deployment. Once that was fixed, we went to another step, and the big images resulted in a long deploy time, not something you actually want. In addition to that, during startup, some of our microservices were taking a lot of resources. Because of long initialization time, some caches being preloaded and so on. And because of that, a noisy neighbor problems actually appeared that the node where the pod was actually deployed was occupied by that service, not the actual production pods that should be working. What's more, the startup time also highlighted the problem of actually Kubernetes forcing us to make a clear difference between the liveness and readiness probes. Because we went into the dead loop basically. A container was starting, it took a long time for initialization, Kubernetes killed it, restarted the same container and so on, and the dead loop continued using all resources on the node that it could. So we would like to share some of the experiences just so you don't have to repeat the same mistakes as we did. So basically what we would like to talk in the next 15 to 20 minutes is differences between Java versions running inside a containerized environment, memory considerations for Java, so heap versus op-heap and versus OS caches and why it is important. Swappiness out of memories and things like that also will be considered. Finally, heap sizing, ordinary object pointers in Java, and garbage collector work. We'll also talk about that. So starting with the Java itself. Apart from the visible thing that you see when you are talking about Java heap memory, so XMS and XMX parameters in Java, there is a thing that you don't see and you need memory for. For example, perm and metaspace requires additional memory. Just-in-time compiler also requires memory for the bytecode. What's more, if you are using Java native interface to interact with the operating system, it also needs additional memory as the new I/O package when you interact with the data. What's more, for example, in multi-threaded environments, when you have a web app that spins a thread for each of your customers or users coming into your application, it needs additional memory, and that needs to be accounted. On the CPU side, we have Java being tuning itself to the number of cores that it sees on the actual machine. So if we have a 64-bit machines, we have 64 just-in-time compiler threads, 64 garbage collector threads, and 64 threads for common fork join pool. And the Java, at least not all versions, are not pretty container aware. So you can actually imagine what happens if you spin up 10 or 20 containers on a 64-core machines that each takes 64 cores for garbage collector. So yeah. So we would like to now show you a demo, actually not to talk about it, but show you a demo about how different Java versions actually behave in a containerized environment. Okay? So as you can see, hopefully that's visible. I can actually make it a bit larger. So we have I have containers actually that are using JDK, and we'll start with Java 7. We'll run the container with 2 constraints, memory up to 128 megs and 1 CPU. Just to keep in mind, this is Mac, so I have my Docker VM here running with the constraints of 2 gigs of RAM and 2 CPU cores, just to visualize the problem. So if we go there, I have 2 classes actually created, very simple. First one, that is about CPU. It just gets a number of available processors that Java sees from the runtime. And let's clear that up, and let's see the second one. And the memory test looks very similar. Just runtime get max memory, and that's all. So let's see what Java 7 sees here. So if we go like that and look at the memory, Java just didn't give any kind of to the constraints put on the container when it comes to Java 7. The same goes with CPU. We would just run on top of the bare hardware that we have. So 2 CPUs there. Let's see how it looks like when it comes to Java 8. Come on, let's change that. Okay. So exactly the same procedure. I'll look at the memory here. So it slightly changed, but still 25% more or less is the maximum amount of RAM that is available by default for Java. And similar to CPUs, we didn't have any kind of changes here, as you can see on the screen right now. However, with Java 8 and its 152 update, we have a possibility of adding additional flags to the process actually. So if we unlock experimental VM options and we use cgroup for memory limit for heap, we actually have some better results. To show you that, if I'll run that memory flags here, you can see actually right now that the new heap memory is actually finally something that we would like to have. However, we need cgroups here. Let's look at Java 9. Okay, let's clear that. And just to keep in mind, this is not using cgroups. So if I'm going to, again, to check the memory, 25% of those 2 gigs that I have, and no constraints are actually put on the container itself. And similar to the CPU, still Java 9. Remember about that. However, with cgroups, it will work. You have to believe me. Now, the things change when we actually are using Java 10 and newer. If we would put like memory test, the same test, we can actually see that the container memory limits are now taken into consideration without any additional flags. And the same finally about the CPU. So we have finally 1 CPU available for the JVM.
All right. So let's jump into into that heap usage. So this is a healthy, like sawtooth pattern. We're going to concentrate on the old generation here because it's typically the more important. So usually heap will just grow with allocations, and then at some configurable threshold, the old GC will kick in and clean some of that up. Now, if those spikes go too high, kind of up and down, then it really means you have too much headroom and you're leaving memory on the table. But of course, you need that headroom because if you don't have enough headroom, the pattern will probably look more like this, which has problems both for performance and for stability. So performance, because the old generation GC will pretty much run all the time if it's always above the threshold. And then stability, because if it does hit 100%, it usually means you run out of memory, at which point all bets are off. Now, let's talk a bit more about GC, and just to be on the same page here, Java heap is typically generational, so new allocated objects go to Eden, and then if they're still needed, they would go through survivor spaces and eventually to the tenure generation, where they get collected by the old generation garbage collector. Now, for garbage collectors, you have 3 main options. and they work well for different use cases. So the parallel garbage collector is the most efficient one, but the pauses will grow with heap. So you'll usually use it for like Rafał showed with to 100 megabytes kind of heap up to a few gigabytes. If you have large heaps, you'll likely want to use G1, which has good throughput and good latency. But the flip side is it will have some remember sets, so you will actually have less usable heap. And CMS is somewhere in between. Its sweet spot is probably around 5 to 10 GB for usually. Now, going further, whenever an object is getting allocated, it has an object pointer, an ordinary object pointer, an OOP, and that matters because usually you would use 64-bit JVMs, and this means you have 64-bit pointers for each object. Now, if the heap is small enough, if it's up to 32 GB, those pointers can be compressed. So let's jump into a little demo and show a bit of that. So here I have a small Docker compose, which will run OpenJDK 11 with, I actually run three instances, one with 30 GB, one with 31, and one with 32. And I choose to print the information on compressed pointers. So you can see that for the 30 GB heap, it says I do have compressed ops, so that's great. I'm having more usable heap. For 31 GB, it's the same, except that they're not zero-based, which means the CPU has to do a bit more work to find those addresses to decode them. And for 32 GB, I don't have any information of any compressed pointers. They're 64-bit, so depending on the use case, it's usually you lose a few gigs. So it's probably having less usable heap space than with, let's say, 30 GB. Now, so far we talked about memory owned by the JVM, whether it's heap or off-heap memory. Now, all that counts against your container limit. But if your application hits the disk a lot, it will likely use mmap. So, for example, Elasticsearch uses mmap by default. And those memory map files are handled by the operating system. So it's part of the operating system cache, which is shared across containers. So it doesn't count against your container limits. So you need to be aware of that and leave headroom for those operating system caches. And one other thing I want to mention is that older Java versions had some leaks when it came to mmap. So that's like another reason to upgrade. And if you have big boxes with lots of processors, they're likely using multiple NUMA nodes. And a NUMA node is a chunk of CPUs which have fast access to a chunk of memory. And Docker isn't NUMA aware, so if you use CPU shares, you might end up in a situation where you have different threads running on different NUMA nodes. So if you want to address that, you can use CPU set to actually assign those threads within the same NUMA node. And you can do much of the same with memory. There's a zone reclaim mode, which tells the operating system to prefer allocating memory within the same NUMA node where your application is. Now, what happens if there's not enough memory for a new allocation? That's when kswapd kicks in, and you can think of it as the kernel's garbage collector. And most likely it will just free up some operating system caches for a new allocation. But the thing to remember here is that kswapd is single-threaded. So that can be a problem if you have big boxes with lots of allocations. So one thing that will help is to start your Java apps with always pre-touch, which will zero out all your heap when it starts. And that's different than just starting it. When it gets the allocation is actually only a promise to the kernel, and when it starts allocating memory, it will actually get it in smaller chunks. Now, if there's not enough memory for the allocation to be satisfied in time, kswapd will try to swap some of that memory. And that's a big no-no for Java apps because Java really expects a fast random access to your heap. But if there's not enough memory to be allocated in time and you have swap disabled, that's when the OOM killer will get invoked. And the OOM killer doesn't necessarily kill the application that asked for that memory, but it kills the application with the highest score. And that score typically highlights the application with a lot of memory usage in the first place.
Okay, so a few lessons learned out of what we actually experienced and what our clients experienced. Use the newest JDK if possible, but remember, be reasonable. Reasonable starts around Java 8, update 152. There are leaks that are fixed that we've mentioned, and with those experimental flags, we can have Java container aware. Going for a newer JDK may require rewriting of your application because of modular architecture that JDK now supports. Garbage collector is not your enemy, at least not always. So keep in mind that this is something that can be tuned. It's not easy, especially for those of us who are not very familiar with Java, but it is tunable and you can actually work. Apart from, for example, 20 to above 20 gigs, as we mentioned, G1 is a good option, so remember about that. Leave as much memory for the operating system caches, especially for those applications that really are depending on the I/O access and fast I/O access. Usually, your application will be less efficient in caching and then removing the cache from the heap than the operating system is. So, for example, Elasticsearch will benefit from it very much. Spread out. We know that this is not a simple problem. Distributed architecture is not easy and sometimes can cause problems, but you will benefit from having smaller containers when it comes to JVMs. Smaller heaps are way easier to manage actually than the ones that are large and require an additional amount of tuning. Allocate your heap during startup. That's once again, you will not encounter out of memories, or if you will, then you will fail fast and you will know what is actually happening. It's better to fail fast than actually have something blown up after 1 or 2 days in your production. Say no to JVM swapping. Once again, this is a key point to have a very good experience with Java. If the memory of the JVM will be swapped, then things go the wrong way. Finally, keep things under observation. You can't fix what you can't measure. You need to have full visibility. And when talking about full visibility, we have at Sematex, we have a product available in SaaS and on-premises model that goes from top to bottom, so from RAM to metrics themselves, so you can take your users, their experience, go through logs, through metrics, through transactions, and have that all in a single panel of glass. If you would like to have a demo or talk to us about that, we have a booth here, so come join us and we'll be happy to give you a demo. Thank you for joining us at the Community Theater and enjoy the conference.
Thank you.